Here's part one of a video lesson on chemical equations, and I'd like to discuss balancing chemical reactions and also the basic types of chemical reactions there are. Maybe you've seen this before, but you can break down water using electricity. Here I have a 9-volt battery, the positive pole and negative pole of the battery, and wires are fed into this system here. These are inverted test tubes with water filled all the way to the top, and here's a beaker that the test tubes are in full of water. Okay, and if we connect to the battery, so let's say we connect to the battery and allow a bit of time, the positively charged wire starts to bubble. Okay, we get little bubbles forming. And the negatively charged wire also starts to bubble. Okay, so this is the positively charged wire because it's hooked up to the positive pole of the battery. And here's the negatively charged wire, and it's negatively charged because it's hooked up to the negative pole of the 9-volt battery. So what happens after a time? Well, those bubbles displace some of the water that's in the test tubes, and so we get some gas caught up in each one of these. After a while, though, we find that we have maybe this much of the one gas and only half as much volume of the other gas collected. It ends up being 2-to-1 ratio. Well, that's interesting. Let's take a look at what's being broken down. Well, water is being broken down, right, by electricity. Electrolysis. Lysis means to break down, electro referring to electricity. So we all know the formula for water, H2O, and it's being broken down. What does it break down into, do you think? Well, it breaks down into these two gases. What do you think those gases are? Well, if we took this gas and actually held a match up to it and allowed it to also be in contact with the oxygen from the air, it would explode. It'd be a small explosion there. And that shows that we have hydrogen gas being formed in tube number 1. So here's tube number 1, here's tube number 2. So in tube number 1 we have hydrogen gas forming. In tube 2, if we took that and let's say we took off a little bit of the straw from a broom that you'd sweep the floor with, and let's say we lit it and got it to smolder and put that in a tube containing this substance here, the broom straw that was smoldering would suddenly burst into flame because now it had plenty of oxygen gas. So oxygen is being collected in tube number 2. So we have hydrogen gas, I'll put G for gas, and oxygen gas being collected from this liquid water. I'll put L for liquid. As you can see from this skeleton of a reaction here, something's wrong. We only have one oxygen atom over here, but we have 2 atoms of oxygen over on this side, and that can't be. Matter must be conserved. It just can't disappear. The hydrogen's okay, but the oxygen's messed up. So what do we need to do? We need to do what's called balance the reaction. So we end up with an equation, equal on both sides, in other words, the same types of elements and same number of atoms on each side. Okay, well, let's go ahead and do it then. The rule for balancing a chemical reaction is to use a large number called a coefficient in front of some of the terms. Okay, so all we can do is multiply by using a coefficient in front of some of these terms. We cannot change the little subscripts. We can't subtract any of these little subscripts or add to them. We can only use big numbers in front, known as coefficients. All right. Well, since we have 2 oxygen atoms on the right-hand side of the arrow, we better try to get the same number on the left. Remember, the only thing I can do is use a multiplier called a coefficient. So I'll try a 2 here. We'll just do a little guess. And I'll just say, okay, I'll put a 2 in front. What does that do? Well, that doubles the number of oxygens. 2 times 1 oxygen gives me 2 oxygens. I'll just write that up here so we can kind of remember what's happening. And that balances out the oxygens on the left-hand side, makes it equal to the number of oxygens on the right. What happened to the hydrogens, though? When I multiplied H2O times 2, that gave us 4 hydrogens. 2 times 2 gives us 4. But we only had 2 hydrogens on the right. So now that I've put this 2 in front, which is a multiplier, it means 2 water molecules, now I have to go back and fix the number of hydrogens on this side. And since I only have 2 on the right and 4 on the left, I need to multiply this hydrogen term by 2. Now we end up with 2 times 2 is 4 hydrogens, which is exactly what we want. This 2 does not multiply across the plus sign because there's no parentheses around the H2 and O2 combination. So this coefficient of 2 here only refers to the hydrogen gas. It does not refer to the oxygen gas. Let's double check. We have 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, and 2 oxygens on the right. This is known as a balanced reaction. It's an equation now, a chemical equation. It has the same numbers of atoms and types of atoms on each side of the arrow. The chemicals on the left side of the arrow are known as the reactant or reactants if there's more than one. To the right of the arrow, these are known as the products, or if there's only one, it'd be a product. So you could have more than one reactant or one, doesn't matter, one or more products. Products are always on the right hand side, reactants are always on the left. So that's the basic principle. Okay, now you try one. Let's say we have something like copper metal, and it's a solid, so I'll put a little S there, which stands for solid. And let's say that we put it in a jar filled with greenish chlorine gas. Chlorine gas, there's 2 chlorine atoms hooked together. Chlorine gas is a diatomic molecule, and it's a gas, so I'll put G there. They react together. And if we give it time, the chlorine atoms and copper atoms will rearrange and form something very interesting. Okay, they will form, well, one thing they would form would be CuCl. Copper 1 chloride. If we think back to the naming, this is copper, Roman numeral 1, chloride. Copper, if we look at the periodic table, has more than one possible charge that it can take on. It can either take on a +1 or a +2. Let's say in this case it had a +1 charge. The chlorine has a -1 charge. it'd just be 1 and 1 adds up to 0. We're in good shape there. So copper 1 chloride is a possibility there. All right. And we can say, let's say this is a solid. Well, is it balanced? Let's check it out. We have 1 copper on the left, 1 copper on the right. So the copper's balanced. But look at the chlorine. We have 2 chlorines on the left and only 1 chlorine on the right. Now what I would like you to do is stop the video for a second and try to finish balancing it on your own, and then turn the video back on and you'll see how we fix it. Okay, stop the video now. Okay, now that you're back and you've tried it, what did you find out? Well, you found out that we need to have a 2 over here, don't we? So that we could have 2 chlorine atoms on the right, just like what we have on the left. And since we doubled this whole thing here of copper chloride, copper 1 chloride, that means we also have 2 copper atoms on the right hand side of the arrow. We go over to the reactant side, we need to double the number of coppers over here. So the balanced equation or balanced reaction is 2 coppers react with 1 molecule of chlorine gas to produce 2 of the copper 1 chlorides. It's a balanced equation, as they would say, or balanced reaction. Okay? So that's the basic idea. Now, I'd like to go over the types of chemical reactions. Next, I'll use RXN as an abbreviation for the word reactions. The types. And we're just going to go over the basic types first. There are other ways of naming chemical reactions, but we'll get to just the basic types. Okay. We have one type that follows this pattern, where we have reactant A plus reactant B form reactant AB. Okay. We see that these combine, don't we? And this is called a combination, or another way of naming it is a synthesis reaction. A combination or a synthesis reaction. Either word will be fine. Some chemical reactions take on this pattern. Reactant AB, just one substance, breaks down to form 2 separate products. 2 or more even. It could be 3 or whatever. Okay, this is just the opposite of the first one, isn't it? It's a breakdown instead of a combination. So this is known as a decomposition reaction. A third type of reaction is where we have maybe one chemical, I'll call it a 1-part chemical, reacting with a 2-part chemical. So this, for example, might be a metal, let's say, or it could be a non-metal. This would be the metal part. This would be the non-metal part of a compound. So the metal part here, non-metal part there. This might be a metal for in this particular example. Those are the reactants. Let's see what the product would be. Well, if this metal happens to be a very active metal, which means it tends to give away electrons very readily, then relative to this metal here, then it's going to be able to take the place of metal B. So we'd end up with metal A taking the place of metal B and hooking onto C, and leaving metal B out in the cold, you might say. This type of process is known as a single replacement reaction. It's also known as single displacement. I'll just write it over here. Single displacement reaction. Single replacement or single displacement, you need to be able to be proficient with both names. Now, instead of being a metal, substance A could be a nonmetal, and in that case, what would we have? Well, we wouldn't end up with a nonmetal replacing a metal, would we? So in this case, if nonmetal A is more reactive than nonmetal C, then A would take the place of C and would hook on to B. So we'd end up with metal B, which connecting to nonmetal A, and then nonmetal C would be left out in the cold. Notice that I always put the metal as the left term and the nonmetal as the right term. Metal first, nonmetal second. Electron giver first, electron grabber second. Okay, so that's the third basic type of chemical reaction. A fourth basic type of chemical reaction would be where you have a two-part compound reacting with another. So we might have compound AB, where we have a metal and a nonmetal, reacting with compound CD. So we have two reactants, compound AB reacting with compound CD. If they're both soluble in the surrounding solution, they might be able to rearrange, and we might end up with something like this. And remember, this is the metal and this is the metals. Metals don't go with metals. Metals go with nonmetals. So what would we have? We'd have metal A possibly going over, see if we can get this thing to work again. The light keeps going out. Metal A going to the nonmetal D, and metal C hooking up with nonmetal B. It's a double switch, isn't it, instead of a single replacement. And so I write the products. I'd write the metal first, so maybe something like metal A hooking on to D, and then metal C hooking on to B. Remember, the metal goes first, nonmetal second. Metal goes first, nonmetal second. So this is known as a double replacement reaction, or, and you can guess, it's also known as a double displacement reaction. The last basic type of chemical reaction I'd like to go over briefly is a type of combustion reaction where carbon is the main ingredient. Okay, a carbon-hydrogen compound. Okay, now there are other types of combustion reactions too where carbon is not involved, but this one is a combustion reaction involving carbon. Here's the basic format for a carbon type of combustion reaction. First, we have to have some kind of carbon-hydrogen compound. It could have oxygen with it too, but I'm just going to put this. And the carbons and hydrogens could vary depending on what carbon-hydrogen compound it was. So I'll just put I'll put little variables on there, X and Y. It could be C2H6 or something, or C3H8 or whatever. But anyway, this is the general format. If we react that with oxygen gas, then and if we do it suddenly, so that we get a lot of heat and light out of the deal, a lot of energy. So heat, light, So a sudden reaction, not a slow simmering one, but where you get a lot of heat, light, maybe some smoke, that kind of thing. That's going to be a combustion reaction. And this one involving carbon and hydrogen, usually. Okay, so what are we going to end up getting? If it's involving both carbon and hydrogen, we have to have carbon and hydrogen and oxygen on the other side too, huh? And so it turns out that the general products would be, if it's complete combustion, we'd end up with CO2 as a product, CO2 gas, and what else? Something with hydrogen and oxygen. That would be water vapor, water gas. So for complete combustion, this is complete combustion, we would end up with CO2 and water as our only two products. If, on the other hand, it was not complete combustion, then we would end up with some intermediate products, some carbon monoxide, some soot, which would be, long chains of carbons and hydrogens hooked together, those kinds of things. But if we're talking complete combustion involving carbon and hydrogen, we'd end up with CO2 and water as our only two products. What if you just had coal without the hydrogen, pure carbon reacting with oxygen? Well, then you'd only end up with CO2. You wouldn't end up with the water part. So if this reactant here only involved carbon without the hydrogen, and it reacted with oxygen, then you'd only get CO2, no water. Okay? So in summary then, we have 5 basic types of chemical reactions. We have a synthesis reaction, and so this follows this pattern. We have decomposition reaction following this pattern here. We have single replacement or single displacement reaction, double replacement reaction or double displacement. We have a double switch, a 2-part compound reacting with another 2-part compound. And then if we have a reaction involving carbon or carbon and hydrogen and oxygen, we end up with CO2 and water. We'll call that a complete combustion reaction. All right? Now let's practice with the 2 reactions we have up here. What kind of reaction would this first one be? The one where water underwent electrolysis and broke up into hydrogen gas and oxygen gas. Look down here and see which one it would be. Which pattern does it follow? We have 1 molecule on the reactant side and 2 molecules on the product side. Well, you guessed it. That's a synthesis reaction, isn't it? Synthesis? No way. That's not synthesis. Sorry about that. It's breaking down. It's just the opposite. It's one molecule breaking down into 2. It's decomposition. That's a decomposition reaction. Okay. So, decomposition, breaking down, one thing breaking down into 2. I'm glad you picked that up before I did. Alright, picked up my mistake. Let's take a look at the second one here. What do we have? We have 2 separate reactants rearranging to form one product. Now we're talking synthesis. That's a synthesis reaction. Synthesis. It's combining more than one thing into one thing. Okay? Let's take a look at another reaction and see if you can figure out what it'll be. Let's take, for example, CH4, which is methane gas. What do you think the products are going to be? Well, it's a carbon-hydrogen molecule reacting with oxygen. This must be combustion. At least if it's fast, if it's a fast reaction, and it gives off heat and light. If it's complete combustion, what would we end up with? CO2 and water. It's left to you to balance this thing out. You can balance that later. What about something like this? What if we have iron reacting with something like silver chloride? What do you think is going to be produced? Think. Here we have a single element, iron. Here we have a two-part compound. If iron is more reactive than silver, it's going to take its place, isn't it? So we could make a hypothesis that this would be a single displacement reaction. And if we follow that line of reasoning, then we'd end up with Fe hooking onto the Cl, and that would leave Ag, silver, by itself. Now, there's one problem with this one, and that is that Cl has a -1 charge, and iron would either be a +2 or a +3. Let's say it was a +3 ion in this case. Then we would end up with 3 chlorines at -1 apiece, neutralizing that one iron ion at a +3. So this is really FeCl3. And that would be left to you to balance this out. We have 3 chlorines on the right, we need 3 chlorines on the left, etc. Thanks a lot, guys. End of part 1.